we just looked at this object, and well, we had it df d tau, but let's just sort of generalize that. Df d lambda, lambda is some parameter, and let's focus on this object because it's important for a specific reason. So this is a scalar, and we got it as a result of a sort of generalized scalar product between two objects, and these are their components. So maybe let's write this out. df the t, let's say t, x, y, and z. dt d lambda, df dx, dx d lambda, df dy, dy d lambda, and df dz, dz d lambda. And of course, this is a scalar, and the idea is it generalizes the dot product, which is ax bx plus, if we're doing x and y, x, y, and z. So here's a space-time generalization. Let's just sort of think of it as space. If we want to add an additional time component, we can do that. But the idea is ay by plus az bz, where we've used, we know that a and b, if we're in x, y, z coordinates, then we have unit vectors associated with these objects, and we're using I dot I is equal to j dot j equals k hat dot k hat, which is equal to 1. And of course, these are all 0. I dot k hat and j dot k hat. These are all equal to 0. And so the problem with these kinds of objects is that in flat space-time, we can associate unit vectors, but in curved space or curved space-time, there are no unit vectors, right? So we want notions. We want to produce a dot product or a generalized dot product that is valid at a single point in space or space-time. And so unit vectors won't work. So we need, tiny little quantities. And this object allows us to construct them or to think of them as resulting from these kinds of objects. So these are sort of the components of these objects. So let's see if we can get some intuition about this. So we can think of the df as, well, it has components, right? df dt, df dx, and so on. So these are like this. So these are the components of this object. And there are some bases associated with this object. So we can write it, it's like saying, ax, or rather, ax comma ay comma az, in saying those are the components, or writing it as ax I hat plus ay j hat plus az k hat. If we write this out, we can see it like this. We can see the the version of this kind of thing, what this object looks like in terms of its basis vectors. Right, the df is df dt dt plus df dx dx plus df dy dy plus df dz dc. And so we can see that there's a basis here that involves dt, dx, dy, dc. And that basis is a quantity that we can imagine being valid at one point. And for the components of this other object, right, this object, right, here are the components there. So this is a vector v beta, and the components are dt by d lambda, dx d lambda, dy d lambda, and dz d lambda. Or we can write this as dt d lambda, right, dt d lambda. We eliminate the f part because it hasn't interacted with the f part, if you want to think of it that way. We have the d by dt, so that we have a more general expression for this object before it then gets to interact with a specific function, in this case f. So we can leave that out, and so it looks like this, plus dx d lambda, d by dx, plus dy d lambda, d by dy, plus dc d lambda, d by dz. And so by the same token, we can see that there's a basis. We can motivate the existence of a basis, which is made up from the coordinates in this way as operators, right? There's a d by dt, d by dx, d by dy, and d by dz at each point, and that serves as the basis. And so this kind of object, this derivative, involves two things that have these components and these components, or these components and these components, if we specify to t, x, y, and z, that can be obtained by thinking of this object like this, with basis vectors like this, valid at one point, and the same thing, but with slightly different basis vectors for this kind of object, and they interact together to give us scalars at individual space-time points.